Oh, our next speaker is Benjamin Baily from Williams, who speaks on large subsets or sumsets. Please go ahead.
Hi, everyone. So I'll be talking about large subsets or sumsets. This work was done jointly with Small in 2015 and 2021 with Justine Dell, Sophia Dever, Adam Dion, Henry Fleischman, Leo Goldmacher, Gal Gross, Faye Jackson, Stephen J. Miller, Ethan Pesikoff, Huituan Pham, Luke Reifenberg, and Vidya Venkatesh. So to start, I will define some of the relevant terms. So given two subsets of the integers, or more generally, any abelian group, we say that their sumset is the set of all sums, one element coming from A and one from B. A short example are these two sets where the sumset is going to be the integers from 0 to 6. We say that a set is reducible if it can be expressed non-trivially as a sum of two smaller sets, and otherwise it's irreducible. And it's important to require that A and B, that neither of them are singletons, because every set is the sum of any singleton with a translated copy of that set. In particular, it's the sum of 0 with itself. So the set 0, 1, 2 is reducible, factoring as 0, 1 plus itself. But 0, 1, 3, as we will prove later on in the talk, is irreducible. And you can prove it's irreducible by checking every possible subset to see whether it sums to it. But we're going to show a procedural way to check it. So we're also going to be talking about subsets of the d-dimensional integer lattice, and reducibility and irreducibility are the same in that context. And just a short demonstration of a sum of two sets in this context is shown below with the dots corresponding to elements of the set. And so to state the main object of study in this talk, we're first defining this piece of notation. So typically in additive combinatorics, the set brackets n denotes the integers from 0 to n. And so this denotes d copies of the integers from 0 to n, the d-dimensional cube of length n. And so the question we're asking, and so we're going to talk about this function, which says, over all the irreducible subsets of the d-dimensional cube with side length n, what is the minimum size of the complement of that set? Now, really, the question we're asking is what's the largest irreducible subset of the d-dimensional cube? And well, it's not the whole cube, but it turns out that it's better to ask what's the minimum size of the complement, because the largest irreducible sets will be very, very close in size to the whole cube. So when we want to talk about this, the size asymptotically, then it's much, we can say much more about the size if we talk about the size of the complement. And we will prove that the size of the complement is asymptotically log n, where the asymptotic log n does depend on d. So this is true for each individual FD, but not true for the FD overall. So first, we'll talk about the largest irreducible subset. So an upper bound on the size of the subset, which is a lower bound on the size of the complement. And so this is an important lemma, like a sort of divisibility test. And if we have a 2-element subset of ZD, then S factors as A plus sumset B, if and only if, for all S in S, both S minus R and S plus R are in S. And so what that means is, in order for the set 0R to not be a summand of S, there has to be an S in S which witnesses that fact, such that both R and S, R minus S and R plus S are not an element of S. And what that means is that if the complement is significantly smaller than log n, then it's too small for this to hold for all R. And as a result, the set is reducible. And we give this specific quantitative bound, where if this bound in terms of the size of the complement holds, then the set is guaranteed to be reducible. And so as a corollary, FD is at least log of n, asymptotically at least. And actually, we can say a little bit more about it, which is that overall FD, this quantity is asymptotically at least d log n. So now we talk about a way of showing, okay, all large subsets of the d-dimensional cube are reducible, but how do you show a set is irreducible? It's a hard problem, actually. In particular, Ki-Hung Kim and Fred Williams-Ruch showed in 2007 that determining if a set is irreducible is NP complete. And so what we've done is we've come up with a stronger condition that doesn't hold for all irreducible sets, but can be checked procedurally and can show that a given set is irreducible. And the definition goes as follows, and we'll talk about first the one-dimensional case, subset to the non-negative integers. If m is the smallest non-zero element of S, then 2m has to not be an S. And for each larger S, other than 0 and m, there is some t smaller than S, such that the sum S plus t is not an element of S. Now, if this holds for all S and S, then S is irreducible. So this condition is called the local irreducibility condition, and if it holds, then S is irreducible. And the way it's defined is defined to be computer verifiable. If S is contained in brackets n, then the verification takes, there's two algorithms. The first takes time equal to the square of the size of the set. There's another algorithm which works better for very dense subsets of n, which takes time proportional to the size of the complement. And irreducibility, there's an iterative argument which follows, and we'll show a specific case of this iterative argument next. And another important thing to mention is that the reason why it's sort of called local is because if it holds for a set and you take the intersection of that set with any interval, then it also holds for that set. So local irreducibility is preserved when you intersect with an interval. And yes, question?
Yes, I'm wondering why for your big O runtime, you have a maximum rather than the minimum. Wouldn't you choose the algorithm that fits better?
Thank you so much for your question. It should be minimum. I made that mistake. Thank you for catching that.
Oh, okay. Good. Just make sure I'm not missing anything.
No, that was great. Thank you so much. Right, so we'll jump into an example of testing local irreducibility. So we're going to show that the set 0, 1, 3, as promised early on, is irreducible. It would be faster to, for this particular example, it would be faster to just check all possibilities, but we're going to show it procedurally. So let's try to factor 0, 1, 3, and it's going to end up that, the only possible factorization is trivial. Without loss of generality, we can put 0 to be the minimum element of both A and B by shifting. And so that means we need 1 in either A or B, so we'll just put 1 in B. Now, since 2 is not an element of S, we can't put 1 in A as well. So next, we're just gonna go on. 2 is not an element of S, so we also can't put 2 in either A or B, because then we'd have the sum 0 plus 2. And finally, since 3 is not an element of, since 4 is not an element of S, we can't put 3 in A, so we have to put 3 in B. And what just happened is everything, one at a time, had to be placed in B. And that's essentially how local irreducibility implies irreducibility works. One at a time, each element is forced to be in the growing set, and the other set is forced to remain 0. So we conclude that 0, 1, 3 is irreducible. And in higher dimensions, the definition goes through very naturally. The only question is, what should we replace the ordering with? There are a couple different possibilities, and the one that ended up working out best for us was the lexicographic ordering. And so we use, and you can actually have a lot of different local irreducibility criteria in higher dimensions, but this one is the most useful. And so we define it essentially analogously. And so now we are going to talk about constructive bounds. So we're going to construct for each cube n to the d, we're going to construct a large locally irreducible subset of that cube. And the way we're going to do that is we're going to construct well, it's going to be one way in one dimension and differently in higher dimensions. In one dimension, we're going to construct an infinite locally irreducible subset, with very sparse complement. And then the intersection of that with any interval is going to be locally irreducible and hence irreducible. In higher dimensions, we're going to place a copy of the one-dimensional set along each axis of the cube, and then we're going to make slight edits until the result is locally irreducible. And so this gives the proposition for all ND, there existing a locally irreducible subset of the d-dimensional cube of length n with size of O log n. And this O does not depend on D. So unlike the overall theorem, which does. And a corollary of this is that f of d is fd of n is asymptotically equal to the log of n. And so now let's go over the construction in one dimension. So when I said pseudo-greedy algorithm, or actually I don't think I said it, I just put it up as a bullet. It starts off with a greedy construction, and then we have to change gears in order to be able to study the size better. So we'll start with this set 0, 1. And the idea is to add as many small integers as we can at each step. So at each stage, we're going to find the largest interval we can add on to the end of our current set. And then so that the resulting set remains locally irreducible, and we set the next iteration of Qi to be that. So to start off, we have 0 and 1. We can't add 2 because 1 plus 1 can't be in the set, 1 being the minimal non-zero element. So we add 3. Note that we couldn't add 3, 4 because we need the local irreducibility condition to hold at 3 because the only candidate is 1. 3 plus 1 needs to not be in the set. The next interval we can add is 5, 6, 7. The reason we don't go further to 8 is because we need 5 plus something to not be in the set. And the only possibility is 5 plus 3. Next, we add 9 and 10. The problem coming up because we need 6 plus something to not be in the set. 6 plus 5 is 11. And we continue. And so now this set, the one that uses the true greedy construction, is locally irreducible by definition. But as mentioned earlier, the set n intersect with Q is also locally irreducible. The problem comes up with estimating the size. We have a conjecture for how this behaves, that the complement of this set is sort of a linear recurrence sequence, but it switches back and forth between 2 different linear recurrences at an unpredictable speed. And so we weren't able to estimate the actual size of this set, but we were able to construct a large irreducible set by slightly modifying the construction. So for I less than 9, we set Pi to be equal to Qi, and we denote this element Ni to be the max plus 1. And for any larger I, we set the max plus 1 to be the sum of the max plus 1 2 earlier and the max plus 1 3 earlier. And then we set Pi to be the previous set adjoined this interval. And we can estimate the size of the set pretty well because the complement in the integers up to n is a linear recurrence sequence. And we are able to estimate the number of terms in a linear recurrence sequence up to n. The way we can do that involves the root of the polynomial x cubed minus x minus 1. And so if lambda is the largest complex root of the polynomial, which is also the only real root of this polynomial, then this sequence grows at the nth term of the sequence is approximately lambda to the n. So the number of terms in the sequence up to n is approximately log base lambda of n, which is asymptotically approximately log of n. And so to recap, we are estimating the minimum size complement of an irreducible subset of the d-dimensional integer cube. And by showing that every sufficiently large subset admits a factorization with some two-element set as a summand, we gave the lower bound. We gave a procedural condition that can show that a set is irreducible, whereas showing that a set is irreducible overall is known to be NP complete and therefore intractable for us. And then we constructed large locally irreducible subsets to prove that, to give an upper bound on the size of fd of n. And we conclude that fd of n is asymptotically log n. And so this research was done as part of the small RU. Thank you to Professors Leo Goldmacher and Stephen J. Miller. This is a photo of small 2021. We couldn't get our hands on one from small 2015. And we also have an OEIS sequence, the largest irreducible subset of the integers up to n. And thank you for listening.
Thank you.